Alright, hi, I'm Zach with HKN. Today I'm going to make a video that's applicable to your systems analysis class, and it's about steady state error. So we have this is kind of an arbitrary system we came up with, but it's a reasonable kind of system to have. We have a third order transfer function in a closed loop. So once we have a closed loop, we can set up a situation where we have a reference input. We can compare our output to the reference input, and we can actually subtract our output from the reference input and then input that, is what we call the error, into our system. So just kind of qualitatively thinking about this, what you'd expect to see, or what we'd like to see, is that we apply an input here, and we'd want to see our output track it. Maybe not perfectly right away, but eventually, as time goes on, we'd want it to get closer and closer to our input, which says that. So if this is our input, if our output is the same as our input, then this little summer right here, this is plus and minus, then this error, if these are the same, this error will equal 0. And so that's an ideal situation. That's what we want. We'll see how close to that we can get. So what we're going to do is we're going to find the steady state error, what the error looks like after a long time. We're going to find that for a few different types of input, a few different orders of input. We'll have a step function, a ramp function, and a parabolic function, and we'll see for each of those what this error looks like after a while. So the first thing we'll need to do is find an expression for error, for the error signal. And we'd like to find one that's applicable, or that's true for any input R of S. So we'll keep this symbolic, and we'll try to find an expression that relates these two. And for the sake of not writing so much on the board, we're going to call this transfer function inside this box, we'll call this G of S. Okay, so let's see if we can just start doing some algebra and find what E of S is. So E of S is equal to what? R of S minus C of S, right? Okay, so that's something, but we can further say that C of S is equal to E of S times G of S, right? So this signal at the output is equal to your input times your transfer function. So we can sub in E of S times G of S for C of S. So we'd have that. E of S is equal to R of S minus E of S times G of S. So now we have E on both sides of our equation. We'd like to cancel this. We'd do a little bit of algebra and get that E of S is equal to R of S over 1 plus G of S. Okay, yeah. So this is an expression that gives us our error for any input R of S, and it takes into account our transfer function. So now we're going to come up with a few different inputs R of S that we could input into the system. Let's see. We'll come up with 3 different ones, and we'll number them 1 to 3. So let's say that let's come up with time domain expressions first, and then find their Laplace transforms, because time domain expressions are easier to think about. So let's say that R1, let's call it R1 of t. Let's say that one was equal to 4, which is sort of arbitrary constant, times u of t, which is a step function. So this is basically This would be just a constant value of 4 starting at t equals 0. So what does this give us? In Laplace, so R1 of S equal to, what's the Laplace transform of the step input? It's 1 over S, and we have a constant multiplier, so that would be 4 over S. Okay, so that's the first input we'll apply. What next? Let's call R2 of t. Now let's kind of increase the order, I guess we could think of it as. You'll see it directly increases the order in Laplace domain, but let's say that we have a input 12t times u of t. So this would be a ramp input with a slope of 12 starting at t equals 0. So our input would just continually grow. So what is this in Laplace domain? That is, so 12 times, call it R2 of S, is equal to, okay, so we have, again, we have an arbitrary constant, and in Laplace, the Laplace transform of t, a ramp input, is 1 over S squared. So this gives us 12 over S squared. Okay, so that's our second input. Let's make our third input R3. Let's increase the order again. So we'd want to see a t squared in our input. Let's just call it t squared. T squared ut, which is just a parabola starting at t equals 0. What does this translate to in Laplace? Okay, so the formula for any, so t to the n in Laplace is n factorial over s to the n plus 1. So in this case, n is 2. So we have, that gives us R3 of s equal to 2 factorial, which is 2, over s to the n plus 1, or s cubed. All right, so now we have 3 Laplace inputs that we can give this system, and we'll actually plug these in one at a time for R of s in this expression. And what did we say we were originally wondering about? We were wondering about what this error looks like after like a significant amount of time has gone by. So what's that saying? It's actually really telling us how close our output is to our input after a significant amount of time. And we'll call that significant amount of time infinity. There's really no such thing as t equals infinity, but we're engineers and we don't really care about the finer points of math. We're just worried about practically what our system looks like after a while. So what we'll use for this, so subbing in these R values, we'll get an expression for E of S, and we'll use something called the final value theorem. I have that written down up here. That says that the limit as t goes into infinity of some time function is equal to the limit as s goes to 0 of s times its Laplace representation, which is really, this is not trivial. This is something that someone proved, and we use it a lot. So that's a good thing to memorize probably. So what we'll do is we'll come up with expressions for E of s with these different inputs, and then we'll do this side of this operation with those expressions to get this, which is what we're looking for. We're looking for what the time expression of error would look like after a long time, or infinity. Okay, so let's say that, let's number our different errors 1 to 3 as well, our different errors from our different inputs. We'll say that E1 of S. E1 of S would be equal to this expression with R of S set to 4 over S. So we'll pull that R of S out front. 4 over S times 1 over 1 plus, actually, let's keep G of S symbolic for the time being, and we'll sub in values, explicit values for it in the next step. Okay, so that's our first expression for our first error. Let's say from the second input, our ramp input, we'll have 12 over S squared times the same expression. And finally, for our third error third input, we'll have an error okay, now we have 3 different expressions for 3 different errors that we get from applying 3 different inputs. And now we'll do the final value theorem with all 3 of these expressions, and we'll see what the errors from all these inputs look like. So I guess we could start working over on this side of it. Okay, so let's do E1 first. So the limit, well, we'll call it E1. Now this is in time domain. E1 of infinity. That's not technically good notation, but we know what we're talking about. That would equal S, never mind, equal the limit. S goes to 0 of, okay, so these are expressions for the error. And what does the final value theorem say? It says we have to multiply those expressions by S. So, so this would equal S times 4 over S times 1 over 1 plus, let's sub in values now, 120 Okay, so now we have to evaluate this at this limit as S goes to 0. So what would happen here? We would get some cancellation right away, right? So this is multiplication here. So these S's would cancel. And then we'd have the limit as S goes to 0 of this expression. Four over 1 plus all this. Okay, so what would happen as S goes to 0 here? These S's that have are in parentheses added to constants. They'd just become that constant. But what do we have? We have this one little S right here hanging out. And as that goes to 0, this term right here goes to infinity. But that term is in the denominator of our total expression. So our total expression as S goes to 0 tends to 0. So that's our steady state error for our first input. So what does that tell us? That tells us that this system, after a while, our system will be tracking a step input perfectly. There'll be no difference between our output and our reference input. So that's really nice. That's ideal. But as we'll see in the next one, we don't always get that. So let's do the second input. So all right, so again, let's do this part of the final value theorem with this expression, or this expression. So we'll have s times 12 over s squared times 1 over that right? Yeah. Okay. So now we have looks pretty similar to our last problem, but what do we see? We see that our input has an s squared in the denominator instead, right? So last time we were able to cancel both of these s's. This time we'll only be able to cancel one of them. So it will become something like that. We'll cross out that s and get rid of this square. All right, let's do some algebra and see how this works out. So, I'm sorry, I didn't write that we're taking the limit of this as s goes to 0. I'll write it over here. So this is going to equal the limit s goes to 0 of. So what could we do with this expression here? We want to rearrange it a little bit to make it. We could move this 12 over the top of that. That's nothing. And let's distribute this little s right here in the denominator, right? We could multiply this 1 times it and then this expression times it. So this total thing goes to 12 over s plus 120 s plus 2. And okay, so we're distributing this s. We'll have s there, and when we multiply this expression, this part of it, by s, this one right here will cancel, right? So this s cancels with this s, and we get down here, we get s plus 3 times s plus 4. Okay. So now we have, that's about as simple as we can get the expression. Let's think about what happens to this as s goes to 0. So as s goes to 0, this term will go to 0, and that's fine. We don't care about that term. It's by itself and getting added. So that's insignificant. Now, as these s's go to 0, this term becomes 2, this term becomes 3, and this term becomes 4. So we have no other terms that completely disappear. So we'll have a finite value, right? So this term simplifies to 12 over this term as s goes to 0 is equal to 20. And that's equal to 0.6. Okay, so that's telling us that for a ramp input, we will have some finite value of error in our output. So after a while of applying this input here, the closest we'll get to it at our output is 0.6. We'll be 0.6 away from it. Okay, let's try our final one here. Let's say we'll call it E3. We're taking the limit as s goes to 0 of s times this term here. S times 2 over s cubed times 1 over okay. So again, one of our s's will cancel. Let's see here. This will equal so this s can cancel out, and we can get an s squared down here now. And we could, let's see, distribute this s squared into, well, we could distribute this whole term in. We'll have 2 up top. We multiply through by s squared on the bottom here. We'll get s squared plus, now when we multiply this term by s squared, not only does it cancel this s out in the bottom, but it adds an s up top, right? So we would get s times 120, and the rest of it same. And the s in the bottom canceled out, so we'd have okay, so what does this term look like as s goes to 0? We would have this term, this s squared term would go to 0. And let's see what happens to this term. This term has an s by itself in the numerator. So it also, as s goes to 0, this term, or the whole denominator, actually goes to 0. So what does that mean? That means that our total expression goes to infinity. It's a pretty bad infinity, but you know. Okay, so we have some pretty interesting results here. We have that our system, since we have some room, I'll try to draw out what these all would sort of look like, or the input and output of our system will look like for each of these inputs. So let's start over here. So we're working in time domain now. And let's apply a step input in time domain. What did we say it had? Amplitude 4. So that's what our input is, right? We picked that. And what do we say our output looks like after a while? We're not really concerned about the transient response, what happens right after we apply this input, but we're more worried about what happens after a while. And we said that the error goes to 0. The error is the difference between the output and input. So that means that, you know, input might look, or the output might look like something like that for a while, but after a while we would be right on top of our input and have no error. So that's good. We like that. So let's try for, say, the ramp input now. We call this so we had a ramp input of that. We picked that. And we decided that after a while, the difference between the output and the input would be 0.6. So our response would probably look something like this. Maybe not track it perfectly for the first little bit, but then it would be parallel to it for the rest of the way. And if we took the distance between there and there, that would be 0.6. And finally, this one is a little bit trivial because, as we see, we go to infinity, but let's try to draw it somewhere. So R3 is a parabola, just t squared. Looks something like that. Well. And we said that our error tends to infinity, which means that our output would probably not track this very well at all. It would probably head off up here, and as this goes to infinity, just the difference between them gets to be, too much. So this is a pretty nice, or not nice, but interesting result. And let's try to backtrack through the problem just a little bit and see what resulted in this this perfect tracking right here. So we had that would be in this term up here. We had some cancellation in the first part of the problem, and then this term, or this term in the denominator, went to infinity as s goes to 0 because of this little s right here. And that's part of our original transfer function. And that's what made the total expression go to 0. So we see that s up here. And what is that? That's an integrator, right? That's a practical thing to be able to put in a system. So if we put 2 integrators in, we'd have s squared here, and we would see that our system could also track this ramp perfectly, and so on and so forth. If we had 3 integrators, it would be able to track this parabola perfectly. So that's a good thing to see from this. I think we refer to that as the type of the system sometimes, the number of integrators in it. So this is a type 1 system. It has 1 integrator. And yeah, so that's pretty much it. So integrators are good for helping us track inputs. So thank you very much. I'll see you next week.